In this video, we're going to take a look at 3 more examples for drawing FBDs. And so I have the first one up for you now. Pause the video and try it on your own before you see how this has worked out. Now I've listed out the questions you should be asking yourself as you go through this. Remember, you want to know, firstly, is this a situation of equilibrium or non-equilibrium? You want to know how many items are touching the object that you're drawing the FBD for, because this is going to limit the number of possible forces which exist. Keep in mind that all forces are contact forces with the exception of gravity at this point in time. And so that's why this is really important. The only force which the only touch which can give you more than one possible force is going to be the normal force, or the force of some other object touching it. For example, with the ground, you can have a normal force which is perpendicular to the ground, and then you can have a parallel force which is friction. Friction is only going to act whenever there's in response to another parallel force which is causing it to want to slide, the object to want to slide. So that's going to lead us to the next question: how many contact forces can exist? And then how many forces do exist? And so then we're going to look for our total number of forces. And this question here, how many do exist, this is in reference to the contact forces. All right, and so then our total number of forces is going to be the contact forces plus the force of gravity. And that's how we get our total number of forces. All right, so you've had plenty of opportunity to read the question, so go ahead and pause the video now, and then we will go through this. Okay, so first let's draw a picture of what's going on. We have a man who is standing in an elevator, and that elevator, of course, is moving in the upward direction. If we're going to draw our FBD, we're going to start by using a box to represent the man and not the elevator. So this is where it's really important that you learn how to separate the object from its environment. Okay, so the first question, let's answer this. Is this a situation of equilibrium or non-equilibrium? And because it's a constant speed and elevators can only move one-dimensional, therefore, yes, it's equilibrium. So basically the acceleration is equal to 0. That's what we get from that. Okay, how many things are touching the man? How many touches do we have? We have 1. There is 1 touch, and that's the touch due to the floor. How many contact forces can exist? All right, now as a result of only this 1 touch, and because it is a touch with the floor, then that means we can have 2 possible forces. But then how many contact forces do exist? That's going to be 1. Because one of these 2, remember that we can have the normal force, which is perpendicular to the surface, and then we have the force of friction, which is parallel to the surface. But because there's nothing that would cause this man to begin to slide parallel to the floor, this force does not exist, the friction force. It is always going to exist in response to another force. So what are the total number of forces that exist? It's going to be 1 contact force plus gravity. So here we get 2 possible forces. So we've already established that we have the normal force, which points straight up. Let's try that one again. And then we have the force of gravity, which is pointing straight down. And that's it. That's all we have for this particular question. So let's move on to the next question. So now we want to draw an FBD for a crane which is lowering a steel I-beam at a constant speed, and the beam is held by a single strand of cable which is located at the center of the beam. As a picture, this is what I'm talking about. We have an I-beam right here, and there's one strand of cable located at the center of the beam so that it's balanced. Take a moment now and draw the FBD. Okay, so the FBD should look like this. First of all, we're going to ask, is this equilibrium or non? And once again, we are in equilibrium because it's a constant speed. We have one touch, and that's going to be due to the cable. And because of that one touch, there's only one possible force that can exist, and that would be the tension force, which points away from the object towards the center of the cable, and it's always going to be parallel to the cable. So we have the tension force pointing straight up, and then we only have one other force that can exist, and that would be the force of gravity, and gravity points straight down towards the center of the Earth. And our FBD is now complete. Okay, in this last example, I want you to draw an FBD for a heavy crate which is being dragged across the floor at a constant speed by a rope which makes an upward angle relative to the ground. So we have a fairly busy problem here, so give this a shot now. Okay, so the first question we're going to ask ourselves, is this a situation of equilibrium or non-equilibrium? And because it is being done at a constant speed, we know that this is going to be equilibrium. And it seems obvious from our diagram here that it's going to be moving in a straight line, the crate. Then we ask ourselves, what is touching the object? Okay, so we have two separate touches. We have a touch here at the ground, and then we have a touch here by the rope. So let's address these one at a time. The rope can only exert one possible force, and that force will point away from the object and parallel to the rope. So there's going to be a tension force which points in this direction. The ground is capable of providing up to two separate forces. One would be the normal force, which is perpendicular to the ground. That force always exists, so we can put that one on our FBD. And then the other force which could exist would be the force of friction. And friction is always in reaction to something else that's going on. So if the crate is sliding and it's a rough surface, then friction will exist. If the crate were not sliding, then it would be reacting. The friction force would be in response to a pulling force. So, for example, if this crate was so heavy and the floor was so rough that this person could not make the crate move, then the friction force would still exist because the tension force is pulling towards the right and it's pulling up. But in this case, it is moving, and so the friction force exists as a result of the slide. So friction is going to point in that direction. We only have one other force, which is a non-contact force, and that would be gravity, and that will always point straight down towards the center of the Earth. Okay, so the FBD is officially done. Everything is on there that we could possibly put on there. This is your official FBD. Now, in green here, I'm going to draw another FBD that I'm going to call a working FBD. And the working FBD is one in which I draw components instead of forces which are at angles at an angle. And that's really, really, really important for the AP exam, because force components have no place on an FBD where they're asking you to draw the FBD. So if they give you a special separate space for drawing an FBD, you never, ever, ever put a force component on there, because a force component is something that we do to better understand or analyze the force which is actually pointing at an angle. So I'm referring right now specifically to the tension force. We know that the tension force is pointing up and to the right. But the tension force has a component which is vertical, and then it has a component which is horizontal. And these components in white, these arrows in white, do not belong on the regular FBD. Now, once they've established, that you've drawn your official FBD in the space provided on the AP exam, then in some other empty space in your exam, feel free to draw whatever diagrams you want. They're not going to grade that in terms of did you draw your FBD correctly. They're only grading the official one that goes in the special space provided. So I recommend working FBDs, especially in the beginning, because it's too easy to forget things. And so on the working FBD, we would have the normal force pointing straight up, the force of gravity pointing straight down, and then we have the tension force, which is pointing straight up, or I should say FTY, the tension force in the y dimension points straight up, and then we have the tension force in the x dimension pointing straight up. Now, friction confuses some people, and if you weren't sure whether or not the friction force existed in this problem or any problem, it doesn't really matter. It all goes back to whether or not you have a net force. Are you in equilibrium or non-equilibrium? Because your FBD describes equilibrium and non-equilibrium if you draw it carefully. And what I mean by that is this. We're told that this is being drug at a constant speed. That indicates that we have a situation of equilibrium. Now, we have to have, because it's equilibrium, we have to have at least one force pointing in, two forces pointing in each dimension. It has to be at least two. So if we look at the vertical dimension, we have the normal force pointing upwards and the tension force pointing upwards, but look, we have gravity which is opposing that. So this is it's plausible that this is a situation of equilibrium depending on how large is the normal force and the tension force and gravity, right? So this is plausible. But when we go to the x dimension, you can see that there's only one force horizontally if I don't draw friction on there. This is a clear indication of non-equilibrium. Go back to your head-to-tail diagrams and let's do one for the x dimension. We've got, if it's equilibrium, we should have Ftx in that dimension, and then head to tail we should have another force that comes back to the origin. So this would be a situation of F net being equal to 0. But if I have a situation where, let me just draw two random vectors, 1 and 2, and then we have a resultant vector, the resultant tells us that we have a net force. Okay? And we know that there is no net force because it's a constant speed. Okay, so we look at this. Ftx there's nothing opposing Ftx. This is clearly a situation of non-equilibrium. Therefore, the only possible other force that could exist is the force of friction. And how do I know that friction is the only other possible force? Well, that's because we have two touches, one due to the rope and one due to the ground. The rope can only provide one force. The ground can provide up to two forces where the normal force will always exist. And that means there's only one other possibility, which is the friction force. Okay, so that tells me that it has to be the friction force. It couldn't be a magnetic force or an electric force or I don't know, a fluid force of some sort. It just couldn't be anything else. By definition, it has to be friction. Okay, so I hope this all made sense, and I hope you got it absolutely correct on the first try. And I hope the information regarding a working FBD versus an official FBD helped clarify some issues regarding the AP exam, and you found it informative. So let me just label this one as official This is what goes on the AP exam in the special space provided. The working FBD is something that you can draw if you want to. I would recommend it at least in the beginning. And as long as you don't put it in your official space, it's completely okay.